On September 1st, 1983, Korean Airlines Flight 007 took off from Anchorage, Alaska, headed for Seoul, South Korea with 269 people on board. Flight operations were relatively normal, but something was terribly wrong. The pilots were reporting the correct coordinates according to the flight plan, but was actually getting further and further off course for over 5 hours. Eventually, the aircraft entered Soviet-controlled airspace without authorizations and was shot down. The flight crew planned to maintain a constant magnetic heading for the first leg of the trip because the first navigation beacon was under maintenance. Once in range of an operational beacon, they switched the autopilot to inertial navigation mode, which follows those beacons. The autopilot never actually started to use those beacons, and the flight crew flew for 5.5 hours without noticing their mistake.
Back in 1983, before the time of GPS, aircraft tracked themselves with something called an inertial navigation system, or INS. INS is a navigation aid that uses accelerometers and gyroscopes to continuously calculate the position, orientation, and velocity of an aircraft without the need for external reference. The INS is a system that knows where it's at in space and time, but the autopilot is a system that controls the aircraft. So these two systems must communicate properly for the aircraft to fly. In order to use the INS, the flight crew must input their beginning coordinates and the coordinates of all the waypoints along the flight path. To use the autopilot, the pilot needs to select one of four modes. Heading mode is needed for takeoff procedures and simply points the plane in the direction of the magnetic heading of the pilot's selection. INS mode uses data provided by the INS to maintain a specific flight path. There's one complicating factor whenever the pilot selects INS mode. The programming first sends the autopilot into an inertial navigation armed mode in which the program checks to make sure the aircraft is both within 7.5 miles of the planned route and pointing in the direction of the planned route. If either of these conditions are not met, the aircraft maintains a magnetic heading as the system continuously checks to see if the two conditions have been met.
Let's take a step back and look at some of the ergonomic factors present during this flight. The pilot had supervisor control of the aircraft, so the pilot was instructing the autopilot and INS to perform the task of flying the plane by setting the controls. The system then determined what information should be displayed to the pilot. According to this table, the pilot supervisor control level was at level 9. The computer does the whole job of flying the plane and tells the pilot what it did and decides what to tell the pilot. The displays of the two systems were fairly rudimentary as previously seen, but those displays and the controls just discussed make up the human-machine interface. The flight crew must monitor the flight of the aircraft for the entire flight, looking for any signal of trouble. The continuous monitoring of this flight is a sustained attention task, and special efforts should be made to make a signal more noticeable in order to mitigate the risk of vigilance decrement. In the case of Korean Airlines Flight 007, the flight crew was receiving an indication that the autopilot wasn't functioning properly, but they failed to recognize this signal. While the aircraft was in inertial navigation armed mode, an indicator light turned yellow. The same yellow as the indicator light that activates as the aircraft passes by beacons, which leads us to our next design failure. While in the distance and time mode, the INS will display coordinates of the beacons according to when the aircraft should have been passing them. Those were the coordinates the pilot reported to air traffic controllers throughout the flight. The incorrect coordinates solidified the flight crew's idea that they were on the right path and pushed their response criterion to the right, and the confusing color coding moved the noise plus signal curve to the left. These two together greatly increased the chance of the flight crew missing the signal.
The design failures can be fixed with better ergonomic designs. The pilot needs to know if the INS is not working properly. This can be done by color coding the light. Instead of the same yellow light used for the other controls, use a flashing red one. You need to help convey the information that is trying to be given. Another design fix would be, instead of displaying the coordinates according to when the aircraft should pass, either display the actual current coordinates, so when the pilot reports to air traffic controllers, they can pick up on the error, or display a warning message that says that they are off path. The design of the automatic navigation mode transmission should make it impossible for the flight crew to make such an error. To prevent the waiting room scenario, the system should alert the flight crew when the autopilot is in INS armed mode for more than 10 minutes. A flag in the system that sets off an urgent, highly detectable emergency signal along with an audible message after 10 minutes of INS being in armed mode. After the suggested emergency alert is activated, the waypoint passage should not update in order to avoid false successful passage. Further, after 20 minutes of flight deviation in the waiting room scenario, autopilot navigation should disengage to force the pilot to correct the deviation. These designs give a warning that is proposed to change the manner in which the act is performed. This needs to be sensed, received, understood, and finally heeded. Also, it is designed to exclude. This is to make it impossible for the pilot to commit the error.